So, I'm going to practice my Japanese. Minasamana konnichiwa. I think that's okay. And so, now, I'm sorry, only English. Ima aigo dake. Gomenasai. So, let's go straight into synchronization planning for 5G. 5G requires anytime, anywhere, always on connections. In order to have good 5G, we will need good timing. 5G will require very high data and bandwidth to the device, to the mobile phone. Seamless, very fast handoff to the mobile phone. Ultra reliability, always on connections to the mobile phone. And a massive number of connections from the network to the mobile phone, which will require many radio heads, big radio density. In order to do this, you will require very good timing. Some of the challenges in the 5G network are around latency. First, in the LTE environment, we have up to 10 milliseconds of latency between the mobile phone and the content. Latency is injected into the signal by the core of the network and at the edge of the network. Most of the latency is at the edge of the network. This will be solved by adding bandwidth and adding connections to the mobile phone at the edge of the network. Also by changing the frame structure of the RF in the 5G environment. So the frame will become, instead of 1 millisecond frame, it will go to a sub-millisecond frame. And the content will be accessed in less than a millisecond. So here are some of the engineering challenges in a 5G environment. We'll start at the top. Here we have massive bandwidth requirements and massive MIMO. MIMO means many antenna. We will have HETnet densification with many small cells deployed around the network. We will need a scalable front haul architecture that will require better synchronization, tighter synchronization. We will have high speed and high security links, double the speed of today's LTE network, with the possibility of connecting at orthogonal speeds of up to 500 kilometers an hour, for example in high-speed trains, rather than 250 kilometers an hour, which is the current specification. And interference management will be required because of the massive increase in connections and the massive increase in the numbers of small cells. All of this means that we will require phase synchronization at the edge of the network. So for phase synchronization, we have to evaluate time error requirements. I'm going to compare the time error requirements between LTE-A and 5G as we go forward. So in a network, it's very simple. You have a conditioned signal taken from a satellite and injected into the network using GNSS and primary time reference clocks. You transport the phase and frequency to the edge of the network, and the network will introduce time error. I was just talking about the time error in the two different environments. The time error is always expressed in nanoseconds from UTC. And then finally the clock will drive the end application. This will be the radio heads at the edge of the network. In an LTE environment, the time error for FDD of course does not exist. We have a frequency network, FDD. We only have a frequency signal requirement of 50 parts per billion. This is basically grandfathered in from GSM, WCDMA, and now LTE, and will still exist going forward for 5G. In the time error requirements, CDMA had requirements of plus or minus 2.5 microseconds, but LTE TDD reduced that to plus or minus 1.5 microseconds, and LTE-A maintains the 1.5 microsecond requirement for various functions, including interference management, massive numbers of antennas, and single frequency networking. The time error requirements in LTE, as you see, are plus or minus 1.5 microseconds. This changes radically as you move into 5G. Some of the functions in 5G, which I will go into some detail about, are carrier aggregation and massive MIMO. In the various carrier aggregation implementations, you will require much tighter time error control than in LTE networks. For example, for contiguous carrier aggregation interband and intra-band non-contiguous carrier aggregation, we have a plus or minus 260 nanoseconds requirement. If you have intra-band contiguous environment, you will have a plus or minus 130 nanoseconds requirement. And if you have massive MIMO between radio heads, you will have a very, very strict, very stringent plus or minus 65 nanoseconds requirement. So the requirements have got very different from LTE to 5G. I'm going to show you this again. 1.5 microseconds at the edge of the network between the radio heads. Anything from plus or minus 65 nanoseconds up to plus or minus 260 nanoseconds at the radio heads. This is a very, very different, much more difficult implementation.